Oh, just to double check too, because we're quiet. Can everyone hear me still now that we're starting? Just get
Yeah.
one. Okay, good. Just want to get one person. Great. All right. So what we're doing is we're moving into chapter 16 now. It's actually it won't be right off the bat, but you're going to see by the end of the chapter that chapter 15 and 16 actually flow very well together. We spent a lot of time on equilibrium and using equilibrium expressions to calculate the concentration of reactants and products at equilibrium. We're going to be doing that a lot now with acids and bases, so it's almost like an applied version of chapter 15. But before we can start that, though, most of what this lecture is going to be is getting definitions under our belt, talking about acid and base reactions, so that next week we can start to get into using ice tables, predicting how strong the solution will be in terms of acidity, will it be acidic or basic. So that's kind of how things will shape up. So hold on a second, it's delayed. Why is it doing that? All right. So if this entire chapter is about acid-base chemistry, well, then we need to get some definitions under our belt. So by the end of the chapter, we'll have 3 different definitions: Arrhenius, Bronste-Lowry, and then Lewis acid-base. So we're going to start with the Arrhenius acid-base definition because it's the most simple. We're going to talk about problems with the definition, and then we'll introduce Bronste-Lowry acid-base chemistry. It's a little bit more powerful definition than the Arrhenius definition, though we'll find out by the time we get to the Lewis acid base that Lewis acids and bases are very generic. We're going to be only looking at hydrogen transfer for the majority of this chapter. So I've kind of given a foreshadow on that. So we've probably used the words acids and bases in our life before, right? But maybe we didn't know chemically why something was an acid or why something was a base, right? So with our definition for an Arrhenius acid, so that's the same guy gave his name to
Professor
the Arrhenius
Cameron,
equation. Yes, what's up?
are you trying to share your screen?
Yeah, and is it not working? Sorry.
Yeah, no.
Oh, you know what it probably is? I've been clicking so many things that it probably stopped sharing. Give me 2 seconds. It says I should be sharing. Let me try it again. Alright, is that better?
It's good now. Yeah.
Alright, and so I see this one person in the chat is probably saying the same thing. Oh yeah, Elena, the lecture is being recorded, so I'll get that up tonight, or today. Alright, so... Good. So we have our definition, so the only thing I really highlighted on the screen, the only thing you missed me do was literally highlight the word Arrhenius acid. So, what is an Arrhenius acid? Like I said, we have phrases where we've called things acidic and basic in our life, but chemically, do we know what that means, right? So our starting definition is going to be any substance that when added to water and it dissociates, it produces the H plus ion. And so what I have down here is just a generic acid. And so you'll see me use this abbreviation a lot. HA is just any acid. So it's a stand-in. We'll do a couple of examples, and this will more come through practice, but we're going to find out that this H here is the thing that's getting transferred. That's the atom that's being transferred between different compounds. When they're reacting, that's going to make something acidic or basic. So that's why we include HA. So if I was going to draw some just generic acid, HA, under the Arrhenius definition, that means when I add it to water, I produce H plus and A minus. As simple as that. So why did I produce A minus though? Because I started with HA. That H is now coming off. If we think about what that H actually represents, right? We know if I drew out, kind of a sketch of what hydrogen looks like, it's a proton with 1 electron. But if we look at H plus, we know that's an ion, so that means it must have lost an electron. And so it's actually just transferring protons. And so I like in acid-base chemistry, you know how in redox chemistry we had to track where electrons were going? So if it was losing it, things were oxidized. If electrons were gained, then it was being reduced. Acid-base chemistry is a similar idea. We're asking, did a proton leave a compound or did a proton gain a compound, right? Oh, sorry, vice versa, a compound gain a proton. So if we're seeing a proton basically being popped off, which I see here, that's like losing a positive charge. So that's why we draw it as A-. So if we look, long story short, the overall charge on our reactants is 0. And if I add up all the charges of my products, the charge is also 0. So I just want to make sure we're keeping track of where everything's going. Before we were keeping track of electrons, now we're keeping track of where protons are going, or H+. So, well actually, I'm going to use that as a transition in a second. So let's go on to Arrhenius bases then. So Arrhenius base is going to be a similar definition. So it's any substance that when added to water and dissociates produces hydroxide, or OH-. And we've seen that before. What we haven't really seen is the nomenclature I've used down at the bottom. There is no element M, but we use it a lot as a stand-in. It's just any generic metal, because that's what M stands for. So it could be sodium hydroxide, potassium hydroxide, something like that. Just an M, it's a metal. And so when it's added to water, it dissociates, so the metal comes off, and then it produces hydroxide. So in both these cases, it's really, really specific, so it doesn't really give us a lot of applicability, right? I mean, it's good, but it doesn't really tell me too much what's going on. And that's why I said we're going to have to increase the sophistication of our definition a bit. One reason, right off the bat, and this is going to transfer us into the next topic of discussion, is it's saying that the way it's written, it looks like H+ just kind of popped off, right? So protons, in general, if they're free, so free protons are unstable. I don't know what the half-life is, but I'm pretty sure it's on the order of minutes, because I'm pretty sure neutrons, their half-life is around 6 to 11 minutes, so protons, I believe, are in the same ballpark. I might be wrong, but I believe it's in the right ballpark. But long story short is if they're unstable, that means when they're just floating around like it's shown here in the Arrhenius acid, they would actually spontaneously decay into quarks. They just literally fall apart. Quarks are unstable, they'll fall apart, and it just turns into subatomic particles. So we know that's not happening when you add acid to water. You're not getting some kind of nuclear reaction. And remember, nuclear reaction doesn't necessarily mean a nuclear explosion. It just means you're having a change in the nucleus. So we've already seen the limitations to this definition. So what we want to do then is expand this definition a little bit. So what this slide is, it's got a lot of words, so we'll walk through it. I don't know why my stuff just froze. Right, so it has a lot on it. So it used to be a more busy slide. I've kind of reduced that. What we'll do on the next slide is I'm going to give you 2 specific examples, and we're going to apply all 3 of these definitions. We'll find out it's actually not that bad. It's easier to do sometimes than say. But let's read through first. So let's see how our definition of an acid has been changed. So we're going to see right away, just like glancing ahead, it's going to be dealing with protons again. But in this case, it's any substance that transfers a hydrogen ion as an H+. Our key phrase is going to be proton donor, right? We said H+ is effectively a proton because it's a hydrogen atom missing an electron, so it's a proton donor. And then if we look to Bronste-Lowry base, it's very different in terms of its definition. Now it's a substance that can accept an H+. We're not even looking at hydroxide right now. So Bronste-Lowry base is going to be a proton acceptor. So we're asking the question, can a compound give up a proton? And can a compound accept a proton? Then we have this definition here. This is going to seem a little vague at first. It's because I changed the slide, but you'll see on the next one when I give you a written example how this is all going to fall into place. So right now, we're just going to read through this definition, and then we'll see how it's applied. So it's a chemical species whose formula differ by only one hydrogen ion. An example would be something like hydrochloric acid and its conjugate. So if this is a Bronste-Lowry acid, its conjugate base would be something that differs by only one hydrogen atom. So this would be an example of a conjugate base. We'll see why it was an acid here and a base here, but just getting the idea that conjugates always come in pairs, these two here, HCl and Cl minus, are a conjugate pair. Alright, so need clarification on definitions yet? I know we haven't done any reactions, but we'll do that in the next slide. Alright. So let's do a couple of examples. So I have it written on the top, BLA and BLB. That just means Bronste-Lowry acid and Bronste-Lowry base. So I'm going to write a reaction up here. I'm going to take that HCl like I showed in the last slide, and I'm going to react it with, let's say, ammonia. What I'm going to ask you, and I'm not going to dump you in the deep end just yet, but what I'm going to ask you is to predict the products. So how would I be able to do that? I'm going to tell you, because right now we don't have enough background, at least in this chapter yet, to be able to identify acids and bases, so I'll have to tell you. By the end of the chapter, you'll be able to do it yourself. But I'm going to tell you, we have a Bronste-Lowry acid, HCl, and it's reacting with the Bronste-Lowry base, NH3. So before we even get into talking about conjugate acids and bases, we're going to save that. Let's just predict the products first. So what I'm going to do is I'm going to start my timer. I'm going to give you guys a minute and 15 seconds, or about a minute. We'll start with that. We'll do a minute. See if you can use your notes and anything else to help predict what the products are going to be. All right, about 10 more seconds. All right. So I know it's a little intimidating trying to do something brand new, but does anyone want to jump on this? Give me one of the products. I don't care which one. There's two of them. So Elena, how are you feeling on this? Could you even just make a guess on what one of the products might be? And if you don't know, that's totally fine. Just let me know. Oh, I forgot you have to type by text and I can't see that. Never mind, sorry. Let's do Gianna. Any ideas?
Ammonium.
Ammonium is definitely one of them. And why don't you get the last one then? There's only two. What's the other one?
Chlorine.
Close. Chlorine, technically, yeah, we had chloride. Good, awesome. It's great that we got that on one go. I 100% agree, right? How did they do that? If you're still wondering, well, we know our acid is going to be a donor, and our base is going to be an acceptor, so that H gets donated to the ammonia, turning it into ammonium. So we've gone from 3 to 4 hydrogens. We lost a hydrogen on the HCl, so it's chloride. So we're in good shape. I'm not going to have you do this one, but when we do this second example, I'll have you do this. So I'm going to have to walk you through this. Let me just get rid of that highlighter. Right, HCl plus ammonia equals chloride plus ammonium. So we're going to talk right now about conjugate pairs. So conjugate, acid, base, pairs. And we're going to see why they come in pairs. So this was my original structure for HCl. If I follow kind of that main structure where I'm not worried about where the proton's going per se, I just care about what was that main structure. Right, the Cl minus was the main part. That's why I'm drawing a line that links these two together. And I'm going to call this now the conjugate base. Why? Because it used to be an acid, and now on the right-hand side of the reaction, it's now a base. We'll talk about in a second why it is a base. But for now, know that it always comes, a conjugate acid, a Bronste-Lowry acid will then always form a base. That is always the case. So then we can apply the same logic. If I had a main structure was NH3, I'm not really caring about protons going around too much, the main structure still looks the same. I have that nitrogen at least with 3 hydrogens. Now I got an extra one. They're a pair, so now this is going to become my conjugate acid. And it's as easy as that, right? Bronste-Lowry acid, it donates its hydrogen. Bronste-Lowry base accepts that hydrogen. Then you take a look at your predicted products and then see which one's the conjugate base, which always came from the original acid. Which one's the conjugate acid, always comes from the original base. The last thing I want to clarify is why do I call it a conjugate base and a conjugate acid? Is because I could theoretically run the reverse reaction. I could take that chloride and re-react it, theoretically, with the ammonium. Oops, I made a mistake. That should be ammonia plus. Ammonium plus, because they're charged. Right, we already went over that. We want to make sure we're transferring hydrogen, H pluses, so it's changing the charge. Right, but I take that chloride, theoretically could re-react it with the ammonium, and then that would reform HCl and ammonia. So under this hypothetical case, this would end up being my base, this would be my acid, theoretically if I ran it in reverse, and then that's what you see here. That's where the name is coming from. But in terms of what my take-home message is for this slide, is anything that's above what I just wrote in black. So everything that I have up there on the slide right now, that's the take-home message of Bronste-Lowry acid, Bronste-Lowry base reactions. So that's going to be our starting point. So I know we've introduced a lot of terms, so I just want to take a pause for a second. Anyone have any questions at all for clarification or anything like that? Or any point that maybe I wasn't clear on that I can clear up? I'm going to have to erase the screen for a second so I can check the chat. Yep, I got chat. Where did my cursor go? Oh, yeah, Jess. No, you caught me on that one. I'm only seeing that now. You're right. NH4 should have the plus charge. All right, so it looks like there's no other questions that I'm at least seeing not in chat, and I'm not seeing or anyone speaking up. The only thing is I lost my cursor. There it goes. All right. Oops, one more in the chat. Oh, great. Awesome. So, oops. Oh, I forgot. There was one more. I wanted to give you guys a practice. That's why I'm like, this doesn't make sense. I wanted to, what does, but I wanted to do a transition. All right, so I'm going to have you both predict the products and label conjugate acid, conjugate base for this particular reaction. I'm going to take ammonia again, but I'm going to react it with water. Oops, water liquid, my bad. Two things, predict the product. And there's two. Then label conjugate acid and conjugate base. So to be able to do that, before we can even start, I have to tell you what's an acid and what's a base. So I'm going to tell you, oops, ammonia is going to be our Bronste-Lowry base, and water will be our Bronste-Lowry acid. Oh, wait. That's not what I wanted to do. Sorry, I'm getting ahead of myself. My bad. Let me just change that from nitric acid. I meant to write nitric acid, not ammonia again. There we go. Sorry. Let's do this one, where this is our Bronste-Lowry acid, and water is our Bronste-Lowry base. So I'm going to give you another minute or so to work on that. So take a look. What's my acid? What's my base? predict the products, and then label the products as either conjugate acid or conjugate base. And one of the products might seem a little funky when you write it down, but trust yourself. All right. So, who wants to jump on this? Even give me the only thing I care about right now is just one of the products. Don't care which one. Give it a shot. Who wants to jump on this? So Maya, you want to give me a hand with this? Just even if you don't know, let me know. But if you got a guess, even what do you think might be one of the products?
I said NO4.
So NO4 I would disagree with, but I like where you're going. We're dealing with the transfer of protons. So you're saying, so say again. Actually, I missed that. You said NO4. So something like this. So in that case, actually, I disagree a lot because that means one of the oxygens would have had to been transferred to the nitric acid. And remember, we're only looking at transfers of protons. So do you want to give it another shot? We have asked. So actually, we even asked this. So for a Bronste-Lowry acid, is that going to be a proton donor, so it gives it away, or is it going to be a proton acceptor, something that takes it? I know it's on the spot. You just learned it.
Gonna be the donor.
It would be the donor, right? And so that tells me that actually the H needs to be transferred over to the water. So instead of being NO4, you keep that main structure of NO3, but I lost a proton, so I'm going to decrease in charge. That's all.
Okay.
So actually, now that I look at it, you were as far off as I thought. You just somehow got the O on there, but you did get the HO.
Yeah.
So you're good. So based on that then, what do you think, and this is the weird one, what do you think the second product's going to be? How do you think I would write that?
Would it be H3O?
Yep.
But then,
yeah,
couldn't you dissociate that? And
actually it won't.
You want us to keep it as H3O.
H3O plus, yeah. So, sorry, it looks weird the way I drew it, but it's a H3O plus, right? Because I gained that proton. So yeah, it actually, that is the structure. It doesn't dissociate anymore from that. If it did, it can give its H up to other water molecules, and we'll talk about that. So it actually tosses it around a lot, but it's effectively staying as hydronium. So in that case, let me just try to write this a little smaller so it doesn't look as funky. And then I'm going to ask someone else to label conjugate acid and conjugate base. So I'll just make that smaller. Then we said we had nitrate and hydronium. So that's more of a foreshadowing. We'll see on the next slide. But hydronium. We're going to see this molecule a lot. This ion. So let's see. Elena, do you want to just give it a shot? The NO3 minus, the nitrate. Do you think that's going to be a conjugate acid or a conjugate base? And I know it's a tough question.
Would it be an acid?
So what's your rationale for that?
Because it has the, I don't know, I feel like normally, I know are usually like acids.
Nope. So the
Okay,
thing
so-
is, like, this is like, it's going to start challenging our presuppositions on things, right? We're used to
Okay.
seeing, like, HNO3 as being an acid, but actually, once it's lost that proton, there's other definitions of acid-base chemistry we could do with it, but with the definitions we have now, we're done. There's no more H that can be transferred. So it's actually, for the nitrate, it's physically impossible to be an acid in our definition. We don't even have to get that deep into it. The way I would go about it to make my life easier is if my main, like, I would say, like, the main structure of this nitric acid is like that NO3. We just know there's an attached acidic proton. That proton goes off to water. So they basically share the same skeleton, and they all, if I told you that's an acid, so even not to like overthink it, it has to be a base. So that's an easy way to get around it too. And then by process of elimination, then, that must mean hydronium is my conjugate acid. That's dumb. So how are we feeling about that right now? And so this is going to come with practice, but like I said, again, what we're seeing on this slide right now is like the take-home message of like pretty much everything we've done so far, except for just defining Arrhenius acid and Arrhenius base. So I'd say this is more like a summary slide, puts everything together. What I do want to use, though, is the introduction of hydronium to kind of segue into this next section. So we're going to see hydronium pop up a lot. And actually, when we get to the pH scale, we're going to find out that's what the pH scale is based on, is on hydronium. So we've already kind of alluded to this, but up here I have a generic acid. It's just dissociating. If I look at it, it's following the Arrhenius definition, right? It's just that H plus is popping off. We already said that free H plus, right, is unstable, so that's not actually what's happening, though. So if this H plus does pop off, well, where does it go? And we already showed on the last slide, it's actually going to go to water and form hydronium. So due to the high reactivity of that H plus, not the instability of it, the part that makes it fall apart, but it's just very reactive. The proton is just very reactive. It's looking for something to bind to or bond to. It's going to find water. So you start with water like this, but then somewhere on it, you're going to attach another proton. Right? So it looks something like that. In real life, what ends up happening is large structures are actually created out of a lot of these hydronium molecules that get near each other. And it's been shown experimentally and computationally that they do form these structures. But for our intents and purposes, we are just going to only use H3O+. And pretty much for the rest of your career, I've never not used H3O+. I've never ever used any of these. That's more for computational stuff, or if you're getting to very, very fine nitty-gritty, maybe physical chemistry, you might need to know that. But for, like I'm saying, for us, and the 99% of most problems you'll come across in chemistry and biology, H3O+ is going to be our water ion, the one that takes the H+. So basically what this slide is, and now it's a little bit out of order because I changed the slides at the last second, but that was basically, this is just a summary of 3 different ways to write that original Bronste-Lowry acid problem I had you do. I gave you specifically HCl, but it follows the same structure. The only difference is A in this case, because it's just a generic acid, has been replaced with chlorine. And so there we go. There's our hydronium, and then my leftover conjugate base. So I don't want to spend too much time on that slide, right? We've actually already done this problem. But just to take us a second to stop and breathe, how are we doing? Any questions, clarifications needed so far? All right. So, what we saw, right, in both examples now, well, actually, no, in 2 different examples, we saw water act as a base and as an acid, right? So let's talk a little bit about this, right? So in this case, this is like the example we did with HCl, right? Or nitric acid, nitric acid reacting with water, right? The H goes to the water, it forms hydronium. Water's a base. I kind of got over my skis a little bit. This is what I'm meaning to say now. Water can also act as an acid. It all depends on what you've mixed together. This is called amphoterism, or amphoteric. So amphoteric means water is both an acid and a base, and it all depends on the situation. We're going to learn what affects those situations. So if I took something that's pretty basic, like ammonia, and I react that with water, so if you went back in your notes, you'd see where I did the HCl ammonia example. But now ammonia, I'm telling you, is still acting as a base. Experimentally, it's been shown to react with water. That means, by definition, water is working as an acid at this point. Why? Because one of its H's is going to be dumped onto the NH3. What does that form? There's my ammonia, and I'm left over with hydroxide. Right? So we see that when water is acting as an acid, its conjugate base is hydroxide. Right now, what I want you to walk away with is being able to predict products, and then also know that water can be both an acid and a base, because we're going to do a lot with this next week. So like let's say, let's keep stuff basic now, and then a lot more application will be next week. So this is not a really good transition. I got to work on that. But what we've done right now is we've defined what an acid is, right? We've started to introduce that, some molecules can behave both as an acid and as a base, but why was water acting as a base under one situation and acid under another? And it actually has to deal with how strong certain acids are, right? It's going to depend. If something's a very strong acid, it will sometimes force things that are weaker than it to act like bases, right? So we'll get more into that, but what we need to do first is define what is a weak acid and what is a strong acid. So, a weak acid, it's going to be an acid that only partially dissociates in water. It's a weak electrolyte. And so, this might be the thing where people freak out. Not freak out. There's crazy people on the internet say things. The idea of you're worried about acid in your body or, whatever. Acids come in various strengths, right? You can drink lemon juice and be fine. That is a pH of 2. It's pretty acidic. If you drank 4 molar HCl, you're going to the hospital, right? Both are acids. Why is one, something you drink on a hot day and the other one almost kills you, right? It's going to deal with how much they dissociate when they are in water. Because if you even think about it, amino acids in your body are acids. Your DNA itself is an acid, right? That's where the A in DNA stands for. So there is a huge variability between strong and weak. So let's skip over this strong figure for a second, just to keep with this idea of weak acids. So we defined what it was. You have a certain starting amount of that HA, that generic acid. Only some of it's going to react with water. So that means there's a good amount of HA left over, and I only made a small amount of hydronium and then whatever the conjugate base is. Right? Again, it's not shown on the screen, but that would be something, a chemical reaction that looks like this. And so there's my A minus and then my hydronium. Right? So it's saying that when it hits equilibrium, I have some HA, I have some A minus, and I have some H3O plus. When we get into doing the ice tables, we'll talk about it, but water, we really don't care. We're going to assume there's so much in excess that I really don't care about its concentration. But take-home message, partial dissociation. Only a small amount is actually converted to hydronium and into A minus. Put that on the flip side then. What makes something a strong acid? Well, effectively it 100% dissociates. So something like HCl. If you add that to water, all of the HCl is actually gone. It turns almost entirely, I won't say it's gone, some of it's there, but over 99.9% of it is in the form of hydronium or A minus. So take-home message. Weak is partial dissociation. Strong is near full dissociation. And I'm going to give you a list of strong acids to memorize, and then everything else other than that is weak. It kind of makes it easy. And that's what I have right here. So the only ones that I'm going to have you memorize, I said, are going to be the 4 strong acids. Oops. So we have perchloric acid, hydrochloric acid, sulfuric acid, and nitric acid. So need to memorize. That's going to be our definition of a strong acid. This definition also, under certain circumstances, also apply to bases, right? Though it gets a little bit more complicated. But I do want you to know what strong bases are, and this more follows the Arrhenius definition. You'll see down here, I got some bases that look a little bit strange, possibly, and we're going to not really deal with those too much. The reason for that is you will come back again in organic chemistry, and then you're going to do a lot with acid-base chemistry that goes a little bit deeper than what we're doing in Gen Chem. So for us, what I want is just hydroxide, and there's going to be a caveat to this. It follows our Arrhenius definition of a metal hydroxide when added to water fully dissociates into M+, which whatever metal is. Maybe it's sodium, maybe it's potassium, and then forms hydroxide. I'm trying to write 100%. It's getting squished. Are we okay with that? So the only things, like I'm saying, that you need to memorize that are strong, these 4, and then know the definition of metal hydroxide will be our strong bases. And so that's how we're going to go forward, at least to start with. Once we get better ways to quantify how to when something's strong. It'll be a little easier. But now it's going to have to be memorization. So just pause, take a breath. Any questions, clarifications on the last couple of slides we did? All right, great. So, let's talk a little bit more about water being both an acid and a base. So the way the segue comes in is that water is both a weak acid and a weak base. So maybe I should clarify that. And that's how we're getting that transition. So it's a weak acid and it's a weak base. So that's why, like when you jump into a swimming pool, you don't dissolve, right? It's not a strong acid, it's not a strong base. It's just weak. Come on, slides. There we go. So we've actually talked about this. I'll just put both up there, right? Depending on the situation, we can see that water is either a base or an acid. Right now, we can't determine when or why. Like I said, we will be able to do that. For now, know that it is both an acid or a base, and it's context dependent, and I'll have to give you that context right now. So let's go a little bit on more with that topic. So which is it? When it's just pure water. Is pure water an acid? Is pure water a base? Right? Because we're talking about water as an acid or a base in the context of a reaction. Well, theoretically, and this is what actually happens, it's been shown experimentally, in pure water, it's completely random, depending on how things react in space. If 2 water molecules, which we have here, smash into each other in pure water, they can form hydronium and hydroxide. Which one acts as an acid, which one acts as a base, we don't really care. We just know we have 2 colliding. So it looks something like this, right? We have our 2 water molecules. That's what we see over here. So there's 1 water molecule, there's another. That slashed line between them just means there's a hydrogen bond. And what we see is 1 bond is broken and then a new one is formed. That leaves us with our hydroxide and our hydronium. So that's more of a visualization. Oops, I went a little bit too quick. What I want you guys to do, spend 30 seconds or so, write me the equilibrium expression. So that means no numbers. Just write me the expression, products over reactants, for this particular reaction. So I'm going to put my timer on. We've only got about 6 more minutes, but we're pretty much where my last class was. So I'll give you a minute to work on this to get me my K.
Can I ask a question?
Yep, go ahead.
So I thought the equilibrium expression only applied to gases.
It's gases and aqueous solutions.
Okay.
Yeah, that's a
Alright,
trick.
thank you.
There's a trick to this one. You're already getting ahead of me on that, but I like where you're going.
Okay.
All right, so we're pretty much at a minute. So does someone want to jump on this? Because we only have about 5 more minutes left. So with all the stuff, actually, let me just do this. I can wipe this and pull this back up. All right, does anyone want to jump on this, what the K expression is going to look like? How about Simran, do you want to jump on this with me? Let's figure out what K equals.
I said K equals H3O plus
Yep.
times HO minus.
I agree. And I like what you didn't include, because that's 100% true. So I agree. What you just wrote now is true. The trick to this, which sounds like a lot, I actually just got from both people who are talking. It's, sorry, I just lost my train of thought. Right. I have a mixture of liquid, liquid, aqueous, aqueous, right? Some students, and I've been guilty of this, sometimes doing it too quick, might put my products on the denominator. But it sounds like to me that people were on board that because water is a pure substance, and this goes back to that slide from chapter 15 on heterogeneous equilibrium, liquids and solids don't belong in the K expression. So we're done with this. So I agree. Was it Jess asked? No, Simran, I asked you. Right? This is our K expression. So Hannah, I see you raised your hand. You have a question? I don't know if you can only type.
No, I was just going to say the same thing for the answer.
All right, great. Awesome. So I'm glad we're all on the same page then. All right, so what I want to do is just kind of introduce a couple more things. We have 3 minutes. Let me see how busy the next slide is. If it's straightforward, we'll just do that. If not, then we might just pause for the day. Sorry. Yeah, it's a little bit busy, so why don't we stop with that? I think that's a good place to stop. We know what KEQ equals. Let me just say the last thing I want to say is that instead of calling it KEQ, we're going to give it a new name called KW, because it's important enough and it will pop up enough that we're giving it its own name. So KW, sometimes what this is called is the autoionization constant of water. All right, so we're pretty much done. So if you have no questions, you're free to log off. I'll stick around for a little bit longer if people have questions. But just remember, you have an entire week off. I'm not going to see you until until next Wednesday. So what I'm trying to do is, make sure you take the day off, at least either on Friday or Monday. At least our department is making sure that you guys actually get the holidays you're supposed to get. So my plan is to not set up any sort of work, so, for Monday or for Friday. All right. So, like I said, if you have any questions, I'll hang around. If not, you're free to head out. Oh, Gianna, your hand's up. What's up?
Is there any extra credit available?
Right now, it's not. I'm not gonna offer that before the decision. By the 9th, I have to talk to Dr. Lau about that. Typically, we don't, but we do need to see what the grades are going to be on the exam.
Okay, thank you.
Mm-hmm. Oh, yeah, Amina. What's up? Oh, chat.
I was confused. So,